This episode is brought to you by Cisco Educational Premium.
The visible universe is mainly composed of fewer than 100 naturally occurring elements. Nevertheless, this limited set of building blocks, called atoms, give rise to an astonishingly diversity of chemical substances, both in the cosmos and within our own body. The reason for this vast array of chemical substances is that atoms rarely exist in isolation. Instead, they predominantly combine with other atoms through chemical bonding, creating an almost limitless array of chemical components and materials. These combinations give rise not only to the multitude of phenomena observed in the universe, but also to the complexity necessary for life, energy sources, consciousness, and other macroscopic processes. The universe is not monotonous because atoms form bonds with each other, resulting in rich chemicals with properties fundamentally different from their constituent atoms. This happens because of the role that energy plays in the formation of molecules rooted in quantum mechanics. Important chemicals in our lives, such as the air we breathe, are composed of molecules rather than individual atoms. Oxygen, for instance, exists as the atomic molecule with two oxygen atoms bound together. Similarly, nitrogen is found as the atomic molecule, and water is H2O, consisting of two hydrogen atoms and one oxygen atom. Atoms predominantly exist as molecules due to their tendency to adopt a state of lowest energy. Just as a marble at the top of the hill will naturally roll down to bottom, all natural systems seek to minimize their potential energy. This principle also explains the unidirectional flow of river from high ground to lower ground. Energy plays a crucial role in the formation of molecules. For instance, when looking at the simplest atom, hydrogen, consisting of one proton and one electron, it is usually found as H2 or hydrogen gas. Quantum mechanics explain how atoms form molecules to achieve lower energy states. When a second hydrogen atom is introduced, interesting interactions occur. As the atom gets closer, the electrons, being negatively charged, repel each other, but they also get affected by the positive charge in the other atom, leading to attraction. There's a balance or sweet spot distance where the protons prefer to be allowing electrons to be shared while minimizing repulsion. The attraction between the atoms is not solely through electronic cloud repulsion. Multiple interactions are at the play. The system's behavior is governed by the total energy of the system, determining how atoms are bound together to form molecules. To determine the lowest energy state of a two-atom system, such as a hydrogen molecule, several factors must be considered. Kinetic energy of each atom and the potential energy between the protons and electrons. These calculations are encapsulated by the Hamiltonian, representing the energy of the system in quantum mechanics. Solving the time-independent Schrödinger equation using the Hamiltonian yields possible values for energy. However, this equation is not easily solvable and is often represented graphically, showing the energy changes as the two atoms move closer together. At a certain point, the graph exhibits a dip, representing the lowest energy state when the atoms are at an optimal distance from each other. In this optimal state, the two atoms are more content being together at a lower energy level than they were separately. This is why hydrogen atom naturally combine to form molecules of H2 rather than remain isolated. Such electron sharing between atoms is known as a covalent bond, and similar covalent bonds form between other atoms. The stability of atoms and their tendency to bind with others are related to the number of electrons in their shells around the nucleus. Atoms with specific numbers of electrons such as 2, 10, 18, 36, 54, or 86 are particularly stable due to the lowest potential energy they possess. These numbers correspond to the electron count of the naturally occurring noble gases, which are chemically inert and do not bind with other atoms. Atoms strive to attain a full valence shell electrons, which involves either sharing of electrons through covalent bonds or transferring electrons through ionic bonds. The attractive force for sharing electrons to achieve a full valence shell is balanced by the repulsive forces between electron clouds and electrons. The explanation for this magical number lies in quantum mechanics, specifically in the Schrödinger equation and the Pauli exclusion principle. The latter states that no two fermions, such as electrons, can occupy the same quantum state, and electrons in same orbitals must have opposite spin. By combining these principles, these specific sequences of numbers are determined as the ones resulting in the lowest potential energy of chemical systems. In complex calculations involving many atoms like in water, approximations like the most potential equation are commonly used. These calculations show bond lengths that leads to the lowest potential energy of the molecule. Ultimately, quantum mechanics helps us to understand how nature behaves, but it doesn't provide the underlying reason on why nature is as it is. It merely illuminates the working of nature without explaining the fundamental why. Neutron stars are some of the extreme entities found in the universe. They appear as colossal atomic nuclei with diameter stretching over kilometers and possessing mind-blowing density and violence. But how can such a phenomenon possibly exist? The existence of a star is intricately balanced between its gravitation force and radiation pressure stemming from fusion reaction at its core. Within a star's core, hydrogen undergoes fusion and transforms into helium. As time passes, the hydrogen supply depletes, and if the star is massive enough, helium begins fusing into carbon. As these massive stars evolve, their cores undergo layering with progressively heavy atomic nuclei accumulating at the center. Carbon further fuses to neon, which further transforms into oxygen and silicon. Ultimately, the fusion process reaches iron, an element that cannot undergo further fusion. When the fusion process halts, the radiation pressure diminishes rapidly, causing the star to lose its equilibrium. If the core mass exceeds about 1 to 4 solar masses, a catastrophic collapse ensues. The other part of the core accelerates with velocities reaching up to 70,000 kilometers per second as it collapses inwards towards the star's center. At this point, all the fundamental forces operating within an atom come into play to counteract gravitational collapse. The quantum mechanical repulsion between electrons is overpowered, leading to electrons and protons to merge into tightly packed neutrons. The other layers of the stars are finally expelled into space during a supernova explosion. Now we witness the emersion of a neutron star. Its mass varies between 1 and 3 times that of our Sun, compressed into a compact object with a diameter of approximately 25 kilometers. It contains the equivalent mass of about 500,000 Earths, akin to the size of Nairobi. The neutron star density is so extreme that 1 cubic centimeter of its material holds the same mass as an iron cube spanning 700 meters across. That explains why the Hawk can not lift me on knee. Sorry guys, just think aloud. Sci-fi. This quantity amounts to roughly 1 billion ton, comparable to Mount Everest mass, confined within the space of a sugar cube. The gravitational pull of a neutron star is remarkably potent as well. Dropping an object from 1 meter above its surface would cause it to hit the star in 1 microsecond and accelerate to velocity of 7.2 million kilometers per hour. The surface of a neutron star displays an exceptional flatness with irregularities not surpassing 5 millimeters. It possesses an extremely thin atmosphere of hot plasma. The neutron star surface reaches approximately 1 million Kelvin, contrasting with our star temperature of 5,800 Kelvin. The crust is incredibly solid and likely composed of ion atom nuclei lattice and dispersed with a sea of electrons. As we approach the core, the number of neutrons increase while protons decrease, eventually resulting in an immense mixture of indistinguishable neutrons. The core of neutron stars remains enigmatic and mysterious. Although we haven't fully grasped their properties, the prevailing belief suggests that they may be composed of superfluid neutron degenerate matter or an ultra-dense quark matter called quark-gluon plasma. These peculiar states of matter defy conventional understanding and can only thrive in ultra-extreme environments. In many aspects, a neutron star bears resemblance to a colossal atomic nucleus, distinguished mainly by the forces binding them together. Atomic cores are governed by strong interaction, while neutron stars are governed by gravity. If it weren't already extreme enough, let's explore some other attributes. Neutron star exhibits incredible fast rotation, with young ones spinning several times per second. If a nearby star is unfortunate enough to be captured by neutron star gravitational pull, it can accelerate its rotation to several hundred times per second. As in the case of PSR J17482446AD, which spins at an approximately 252 million kilometers per hour, this rapid rotation leads to a peculiar star-shaped. We designate these objects as pulsars due to their emission of strong radio signals. Additionally, the magnetic field of a neutron star is approximately 8 trillion times stronger than Earth's magnetic field. This magnetic force is so potent that it bends the path of atoms as they come under its influence.
Cisco Educational Premium is a section of Cisco Educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals.